let's go ahead and get started today. So I've got lab posted for this week. We're going to do an alum lab, which is alum is a mineral that contains aluminum as the base metal in it. We're going to synthesize alum and look at our percent yield. So we're actually going to take some aluminum cans, digest them in a base, and then create that mineral. And it's a two-part lab, so we'll do part of it tomorrow, let the material set, and then come back and finish the lab up on Thursday. We're going to work towards finishing probably chapter 11 is one of the longest chapters, just to let you think about timelines. This is the start of the third week of class. We're going to take our first exam at the end of 4 weeks. So we're halfway through the first exam. So I'd like to be a little bit further, but we start a little bit slow and then we gain speed as we go. You'll get used to the way I teach, and I will start doing things at a little bit faster pace. Just the Mastering Chemistry, Chapter 11, Part 2 is available. You can start working on that. It's due not tomorrow, but a week from tomorrow. So you've got to the 4th to work on that. So the last thing that we looked at, so we're talking about intermolecular properties and the attractive forces between neighboring molecules, and we were talking about this relationship between cohesion and adhesion. And we said cohesion is the attraction between like molecules, or that substance, and adhesion is attraction between unlike substances. One way that's really, we talked about the capillary action, and then we could look at the shape of the meniscus being different. A good example of seeing this to quickly determine something about the types of forces is you can take a capillary tube that's made out of silica, which is polar, and if you put it into water, the water will climb up the capillary tube with capillary action, and the meniscus will be a curve down. So that's a good example of adhesion. But if I stick that same capillary tube in a pool of mercury, or some liquid mercury, what happens is it actually pushes the capillary in, and the liquid doesn't even come up to the level because of the strong properties of adhesion. Weakness of adhesion, the strongest property is cohesion. The mercury wants to be near itself instead of being near the surface where it's polar, because mercury is a nonpolar molecule. So we can learn some things about physical properties just by doing some simple physical tests and understanding what occurs with what we observe. So we're going to start talking about the process of vaporization and going from a liquid to a gaseous phase, and that's a topic for probably the next day and a half at least. We talk about liquids; they're constantly in motion, not like solids that are locked in place. They have vibrations and rotations, and they can translate, means move in three-dimensional space to some degree. We know that the amount of motion is related to the kinetic energy, which is proportional to the temperature. What happens is that some of the molecules, they vary in the amount of kinetic energy they have. If you remember that plot of kinetic energy versus temperature, where temp is on the x-axis and kinetic energy is on the y-axis, at any temperature, it's a distribution. So there's an average, but there's some molecules that are down here that are below, and there's going to be some molecules that are higher kinetic energy at any given temperature. So we talk about averages, but there's still some proportion of the molecules that are higher and lower than others. When we talk about the process of vaporization, we want to know if there's enough of the high energy molecules on the surface. What happens is they get enough energy that they can overcome the attractive forces. So these molecules, basically, if you want to think of them, they're sitting on the surface and they're shaking. All right, so you're trying to hold back 15 kindergartners trying to get to the suckers. All right, so they're shaking, they're trying to move, they get loose, and if they can get enough energy, they break loose into the vapor phase. Okay, so that's kind of the idea of what's going on for molecules that don't have enough energy. They can't break loose, they stay trapped in the liquid, but the few that have enough kinetic energy, they escape out into the vapor phase. So what happens when we spread the surface area out? We get a faster rate of vaporization because we get a larger surface area, we just get proportionally a larger number of molecules that have that higher kinetic energy that can escape out into the vapor phase and escape from the liquid. So what happens is this process of becoming a vapor is related to a number of different factors. One of those factors, the strength or stickiness and how well they stick together, is a measure of the intermolecular forces. Now, when we think about what's happening with the molecules, typically only a small fraction of the molecules have enough energy that they can break free from the surface. But that changes with temperature. And we call the amount of energy required to get free, we call that the escape energy. And it increases with temperature. The higher the temperature, the higher the rate of vaporization. We can see this on the summer. You drop some water on a hot sidewalk, and you look back in a minute, and it's completely vaporized. And when the winter was cooler, you drop that water, and you come back in an hour, and you still see the traces of the liquid there. So what's going on with that? If we compare a low temperature in blue versus the higher temperature in red, the blue represents this kinetic energy and the fraction of the molecules that have enough energy to escape. So this is the threshold that's required. It's the minimum energy needed to break free from the surface of the liquid, okay, and to go into the vapor state. So at a low temperature, this may be a very, very small percentage. But as the temperature increases, this whole distribution shifts in the up direction to the right, and that percentage now increases substantially. If we'll keep taking the temperature up, we could get it so most of the molecules have enough energy to do that. So that's what's happening whenever we change the temperature. We're just changing the number of molecules that have enough kinetic energy to escape. So whenever if we think about the process, as we talked about vaporization, that's when something escapes. If we go the opposite direction, when a vapor molecule loses energy through collisions, sometimes if it strikes back in that surface, it gets captured back in the liquid when it collides with the liquid surface. So the same way that we think about that, if we imagine that motion occurring, so if we have a liquid on a surface, be blue. Okay, so we've got some water in our container, and some of that water escapes out in the gas phase. It's going off in all directions. Occasionally, some of those water molecules are going to be headed back and would strike the surface. And depending when it strikes the surface, it depends on how much kinetic energy it has. If it doesn't have enough kinetic energy, it'll get captured back in the liquid. That's what the condensation process is. So it gets stuck to the molecules around it. It becomes part of that liquid again. It can happen anywhere where the molecules could bind together. So if you had a collision between two molecules and they could stick together up here and become a droplet, and then more molecules might adhere to that. We had an excellent example of that happening today. It's still here. That's what our fog is. So it's conditions where the vapor pressure and the temperature combine to the point where water molecules in the air that's normally in the vapor phase is transparent, we don't see it, form these small droplets. Okay, so that's, I hope there's not a wreck on 75 or somewhere where there's a lot of traffic like there was a few weeks ago to the fog. It's pretty poor visibility. Things like fog probably played a role in the helicopter crash yesterday with Kobe Bryant. Yes?
You put like a glass of water in like a really, really humid environment, would it like with more water form inside the glass?
It depends on the vapor pressure. That absolutely can happen. We'll talk about it in the upcoming chapters. On the solutions chapter, you can actually create solutions that are thirsty. And if you had a closed container, let me go back to my page that I was drawing on. If you took a closed system, right? So you put a container over something, and you've got two different beakers that have water in them. All right. If you can sometimes put something in one solution, and the water vapor would transfer from one to the other. So if you came back the next day, this water level would be down to here, and this one would be up here. Absolutely, that can happen. Okay, so we call those thirsty solutions, but we'll talk about the why behind that as we go forwards. All right, so when we think about this concept of condensation versus vaporization, it's a two-way process. So it's going in one way, it's going out, losing energy off. So in the condensation is the opposite direction, and energetics play a role as much as these intermolecular forces. So the two processes are essentially just opposite of one another. Okay, and if we think about what happens in an open container, so if there's no lid, no top to it, the vapor molecules escape out into the room, and what happens with that is they spread out faster than they can condense back out. So if I put a beaker of water with 100 mils on it and the count on the table in here, if I came back tomorrow, almost all of that 100 mils is going to be evaporated, if not all of it. Okay, it depends on what the room temperature is. So the net result of vaporization, the rate that it occurs, is greater than that of condensation, so there's a net loss of the liquid. However, if I close the container, I put a lid on it, put a piece of parafilm or something on the top of it, the vapor can't continue to spread out. So now what happens is there's no indefinite volume associated with it. So the closed container at some point is going to reach a point where the rate of vaporization and condensation become equal to each other. It stops evaporating. So just the head space on the surface above the liquid gets saturated, and then the process slows down. Where the intermolecular forces play a role is that the weaker the attractive forces between the neighboring molecules, the less energy it takes to escape. So it's a direct relationship for the strength of these intermolecular forces. We talked about it, how it affects things like viscosity last week. So now we can take that same type of thing and apply it to the process of condensation and vaporization. So also the weaker the attractive forces means that the more energy is needed to remove the vapor and to condense it. So if you've got something in the vapor phase and you want to condense it, it's going to take more energy to squeeze those things together once they're separated apart. So what we see is that in the vapor phase, comparing a vapor and a liquid, that the liquid is going to evaporate faster. That means that it has weaker attractive forces, and then it's going to have a faster rate of evaporization. So the things that have the stronger intermolecular forces, they're slow to evaporate. Weaker forces are faster to evaporate. So things that have the weakest intermolecular forces that evaporate very easily, we give the term volatile. Examples of that are things like gasoline. You've all been at the gasoline pump, or more than likely, and you've spilled some gasoline on the ground. If you watch it for a matter of seconds, the evaporating gasoline hits the ground or drips down the side of your car and evaporates out. It's completely gone. Because the vapor pressure is extremely low, the energy between those molecules, the intermolecular forces, is low. The same is true of acetone, fingernail polish remover. Liquids that don't do this, that have high intermolecular forces, are called non-volatiles. So examples of this are something like motor oil. If you took motor oil and poured it out in a beaker in an open room, you can come back in a year and 99% of the volume is still going to be there. Okay? Because it doesn't transfer into the vapor phase unless you really, really heat it up. So when we think about the energetics that are occurring, if we think about the high energy molecules, the ones that have enough energy to escape from the surface, when they're lost from the liquid, the average kinetic energy of the liquid decreases. And if that energy is not drawn back into the liquids from some external source, the temperature of the liquid is going to decrease. So what that tells us is the vaporization process is an endothermic process. Those of you that played sports, you know what a frog tog is. Okay, so a frog tog is something where it puts a high surface area of liquid onto you. The way that it feels so cooling and reduces the body temperature so much is that as the liquid molecules from that evaporate out, it takes the liquid is heated up by your body temperature, and as those escape out into the vapor phase, the fact that it's an endothermic process, it takes the heat from your body, from your neck, your head, wherever you've got it out. And it takes that energy with it. It transfers the heat from you to the molecules that go out in the gas phase, and it gets them away from you. They go out in the environment wherever the room is. Now, the opposite of this process is true as well. So condensation is an exothermic. So whenever we take a volatilize, we have to input some energy into it to overcome the attractive forces between neighboring molecules. But the opposite is true. If we want to condensate, we have to take that energy away from it. So the heat of vaporization is the amount of heat energy that's required to vaporize 1 mole of a liquid, and we give that delta H. Change in enthalpy was H, but heat of vaporization, and then VAP represents for a vapor. And it's sometimes called the enthalpy of vaporization. It's always an endothermic process, therefore the sign of it is a positive sign. And it's a little bit temperature dependent. And one way that, if we think about the processes that occur, we said that condensation and vaporization were the opposites of each other, and the enthalpy change is nothing different than the sign. So if we think about what the enthalpy of condensation is, it's just whatever it is of vaporization, and we would change the sign. So if we compare water, so water at the boiling point of water, which is 100 degrees, is 40.7 for the vaporization. So if I wanted to know what the enthalpy of condensation was at this, the enthalpy of condensation for this temperature would simply be a negative 40.7. So the condensation would be a negative 40.7 kilojoules per mole. Okay, so if we do a comparison of some of the different temperatures, that's where it becomes dependent on what the intermolecular forces are. So looking at water, how much it changes from room temperature versus its normal boiling point. So water, its normal boiling point is 100 degrees. We all know that. At that temperature, it's 40.7. If we take it down to closer to room temperature, 25 degrees, it increases the enthalpy of vaporization to 44. Not a huge change, all right? If we look at something like rubbing alcohol, isopropyl alcohol, its boiling point's a little lower. It's 82 Celsius. Its enthalpy of vaporization is almost the same, just a little increase as temperature goes down. If we look at things that have smaller intermolecular forces, so something like acetone or diethyl ether, because lower intermolecular forces, they have lower boiling points. But if we look at the change, usually the change is a little bit less. So the lower the intermolecular forces, the lower the difference between the enthalpy of vaporization at the boiling point versus room temperature. So I want to work a problem. Somebody had emailed me, and my email was down, so I couldn't answer that. I had to do a password update. So somebody had asked me how to do one of the clicker or the mastering chemistry questions. So the question, I'm going to paraphrase this greatly. So it wanted to know how much energy in kilojoules is required to vaporize a certain mass of water. And I'm going to say mine was 1.5 kilograms. All right, so yours is probably going to be slightly different. So to answer this, the relationship or formula we have is that Q is equal to N times the molar heat of vaporization, where N represents the number of moles. So what we're going to have to do is take the mass that's given to us and take mass and convert it into moles. And our relationship that does that is the molar mass of that substance. Okay? So if we want to do this for doing it in dimensional analysis, we can start with what we know. We've got 1.5 kilograms. So we've got 1.5 kilograms.
What does the Q stand for?
The first thing we need to do is to convert that from kilograms to grams. So do dimensional analysis. So 1 kilogram is 10 to the third grams. And now we've got the mass of water in grams. This is the number of grams of water. If we look up the molar mass of water or calculate it out, it's 18.02 grams of water per 1 mole of water. And then we simply, now we've got the number of moles, we would multiply it by the molar heat of vaporization, which is 40.7 kilojoules per mole. Now you're going to learn, if you didn't have me last semester, that I'm big on dimensional analysis, showing your units. Because that's the way it tells you if you have the problem set up correct or not. So Q represents heat. So I can track if I've got this problem set up right by tracing my units in dimensional analysis. Kilograms, top and bottom, cancel out. Grams of water, top and bottom, cancel out. Moles of water, top and bottom, cancel out. The only thing I'm left with are kilojoules. That's what I'm looking for in the problem. So if I multiply everything on top, divide by everything on bottom, that would tell me the number of kilojoules that would require for this transition. So, and I'll just multiply this one out so we know what the number would be. And it would be around, oops, 3388, but we only know it to three significant figures. We think our weakest link rule in significant figures, so we need to express that as 3.39 times 10 to the third kilojoules. Does anybody have a question on that?
How do we get the 40.7 again?
Sure. That comes directly off the table. So that's this number off the table. Yep. It has to either be given to you or you have to look it up at the table. So the molar heat of vaporization is a known. Now there may be a problem where you know the temperature or you know the amount of the substance and you know the amount of heat involved. We use that to determine what this is. So we do that in a calorimeter. So look at the temperature change as a vaporization occurs. But most of the stuff we're doing in Gen Chem, this is a given. It's a known and a problem.
So without a calorimeter,
The molar heat of vaporization, you actually more commonly do it a different way, and that's what we're going to get there today. So you do it with a fun equation called the Clausius-Clapeyron equation. So we're going to dive neck deep into the math. Okay, so here's another example. So calculate the mass of water that could be vaporized by a certain quantity of heat at 100 degrees. So on this time, we're just looking for a different variable. We know what the heat is, or the amount of heat. It's 155 kilojoules. We know what the molar heat of vaporization is. That's our 40.7 kilojoules per mole. Now we want to solve it for the different variable. We want to solve for what is the number of moles and take that into mass. The key to working this problem is realizing that the mass is directly proportional to the number of moles in. So we have to solve this for what is the number of moles, then convert it into mass to do the problem. So let's do exactly that. All right, so if we take our base equation, Q is equal to N delta H, vaporization. I prefer to do problems where I do the algebra up front. You can do the algebra at the end. When you write the numbers out, it doesn't matter, but I would set this up where I would divide it first. So I would divide both sides by delta heat of vaporization. Let that cancel out, and that would give me N is equal to Q divided by molar heat of vaporization. And that's how I would start working this problem. So N is equal to Q, which is 155 kilojoules. And here's where it's important to set your units up. 40.7 is the molar heat of vaporization. Kilojoules per mole. Kilojoules top and bottom cancel out. The moles are on the bottom of the fraction, so they go to the top. So when I divide that, that's going to give me the number of moles, but I really want to know the number of grams. So I just need to convert from number of moles to the number of grams, or the mass. And I use that, do that with the molar mass. So I set to know which one goes on the top. I want the units to cancel out. 18.02 grams of water per 1 mole of water. That allows my moles of water to cancel out. Only thing I'm left with are grams of water in my dimensional analysis. Got my answer. And go into 3 significant figures. 68.6 grams of water. Right. If it would have been at 25 degrees, okay, just a variation of the problem you might have to look for. If instead of at 100 at 25 degrees, the way I would have to change the problem is I would have to use the molar heat of vaporization at 25 degrees. So if that were the case, I would have to put in delta H vaporization was the 44.0. Okay. So that's the one small factor you may look at in those problems. It's not always, it's temperature dependent. And we're going to learn about the temperature dependence as we go on. Yes?
So if the temperature changes, it tell us how much heat or what would be vaporized with?
You would have to work it, if temperature changes, you'd have to be given the delta heat of vaporization. We're actually going to, the next topic we're going to look at is how we can calculate the delta heat of vaporization. So there's a way that we can deal with that if we have enough data in the background. Most of these problems, either data is given to you or you're given a table on almost all of them. Now, some of the problems I'll tell you in mastering chemistry, it refers back to tables that are in the textbook, and it doesn't tell you that information. So make sure you're somewhere in your notes you put to refer to this table 1117. It tells you for these substances, and you've got at least a couple of those in your mastering chemistry. Okay, so you can go back to the textbook, pull that table up, or you can look at it in the notes. So you've got the PowerPoint notes, you can just pull the table up directly from that. But the mastering chemistry asks for some of those problems as well. Okay, so this is a simple one, doesn't require a calculation. So I want you to choose the substance that has the strongest intermolecular forces, and I'm giving you the molar heat of vaporization. So your hint, it's the highest or the lowest number. 1 to 6. Not. Okay, 3 more. Last 2. Last chance. Okay. You either put C or D. D was the most prevalent answer. So the one with the strongest intermolecular forces, most of you said it was choice D, which was the largest. If we look at it, that's the correct answer. So the one with the highest intermolecular forces is the one that has the highest molar heat of vaporization, delta H. Okay, question on that. And the opposite is going to be true. If it's the weakest intermolecular forces, it would have been the one that was the lowest, choice C. Right. Okay, so you'll probably see a question like that either on the final exam or the exam 1 that's coming up. So the next one is now do a calculation. I'm going to let y'all do this as a group. So, open it up. I want to know how much energy is required to vaporize a certain mass of the substance dichloromethane at its boiling point, and I give you the molar heat of vaporization. And you can ask a neighbor on how to do this. I'll give you a couple of minutes to crank it out. So I'll give you the formula down on the bottom. All right. I give you the amount of the mass of the substance, the molar mass, and the molar heat of vaporization. You got everything that you need to work this problem. And again, turn around, talk to somebody, ask a question if you don't know. Confirm your answer with your neighbors, however you want to do it. But got a couple minutes to figure it out.
Wait, so the mm is the molar mass?
MM is molar mass. And I'll typically on exams, I'm assuming that in Gen Chem 1, we learned how to calculate molar mass. I'll give those things to you. I don't want you to waste your time calculating molar masses by adding up elements on the periodic table.
Is that supposed to be 31 kilojoules or joules?
It is the kilojoules. Apologize. Missed that. And that would make all the difference in the world. Yeah. So I encourage y'all to start taking advantage of these group activities. Ask questions of each other. That's how your learning works.
I don't know. What I got that.
Multiply it by the how many moles you have. That's the molar mass of where it's 38 grams. And then multiply by vaporization.
That's grams. Times.
Should be a little more than half.
Oh.
I need two more. All right, so we're all in. Okay, we had 11 votes. So, all right, so most of you went with choice A, and I think I like choice A as well. Just so you see how to do it, usually if 90% of the class gets it, I consider that conquered. But I'm just quickly going to show you how to set this up with dimensional analysis. We're looking for Q. So we need to start with what we know. We're given an amount of sample, so we've got 48.7 grams of dichloromethane. It has a molar mass. We need to convert grams into moles of 84.93 grams of that substance per 1 mole of that substance. Now we've got number of moles. We simply multiply by the molar heat of vaporization, 31.6 kilojoules per mole. And when we do that, just following our dimensional analysis, grams, top and bottom cancel out, moles, top and bottom cancel out. We're left with kilojoules, which once we correct, that's what we get for our right units, and that gives you the 18 kilojoules. Okay, and again, even something like that seems so simplistic, you don't need to use dimensional analysis. Get in the habit of it. The thing that I'll show you or tell you on the exam questions, so if you look at my types of, or my exams, all of the unit exams we're going to take are going to be 25 questions multiple choice, 6 questions on the back that are completion. And I give you partial credit if you show me how you're working the problem. So like if this is in my mind a 2-step conversion, so if you missed like one component of this, you still could get 3 or 4 points out of it. But if all you do is write down this number and you write down the wrong number, you get 0 points out of it. And so showing me your work, showing me you're going through the dimensional analysis can go a long ways. Okay, so now we can do the calculations at a given temperature. We want to think about this process that's occurring, this dynamic equilibrium. So if we take a closed container and the process to start, so vaporization starts to occur, then condensation starts to occur. If those two things are occurring equally, what happens is the amount of vapor in liquid won't change. So if we think about, here's a container, we pour some liquid into it. The moment we pour the liquid into it and put the lid on top of it, immediately it starts evaporating at that temperature. But because there's not liquid in the vapor phase initially, the rate of condensation initially is 0, but as soon as there starts to become some vapor present, then it starts to condensate at a slow rate. As there gets to be more and more vapor, that condensation rate increases and increases until the point where the rate of condensation equals the rate of vaporization. And that's when you've reached the point of the dynamic equilibrium. When the two things are opposite but equal, that's when there's no net change, either gain or loss of either the liquid or the vapor. So at that point, we represent the system by these two arrows, one going forward, one in reverse, and that represents a dynamic equilibrium. The rate of vaporization equals the rate of condensation. There's no net change that's occurring. And we'll talk about equilibrium in detail in Unit 3. So if we think about visually what's going on, or a graphical example of that, you pour the liquid in, put the stopper in it, immediately what's happening is it's just going into the gas phase to start with. Once it's going to the gas phase a little bit, some of the liquid starts to come back in to be condensed. Once the surface becomes saturated with gas, or the vapor becomes saturated with gas, then the rate of loss equals the rate of gain, and there's no net change in the volume of the liquid or the amount of gas. So now we want to think about the energetics of what's behind that. So when we think about vapor pressure is the pressure exerted on a vapor that's reached this point of dynamic equilibrium. That's what vapor pressure means. Now remember when we talked about gases way back in Chapter 5 and Dalton's law of partial pressures, whenever we trap the gas in a vapor, in a water, that water vapor contributes to the overall pressure of the gas. So Dalton's law of partial pressure said that the pressure of a gas total was equal to the summation of the individual components. So it's pressure that comes from component A plus B plus whatever all the gases were. And if one of those was water vapor, then it would have been partial pressure of water contributed to it too. And the way that we corrected for that is we knew what the vapor pressure of water was at the given temperature. Okay, so we knew at 28 degrees what that contribution from water was, so we could simply subtract it out and find out what the pressure of the gas was. With water, we have an exact table that we could apply and figure out what these are. When we start comparing to other solvents, the weaker the attractive forces for the molecule, the more molecules are going to be in the vapor state. So the weaker the attractive forces, the higher the vapor pressure is going to be for a substance. So the higher the vapor pressure, the more volatile that liquid is when we compare to volatility of substances. Now we look at how does it change or respond. So if we use the concept of the piston in Gen Chem 1 with gases, where if we had something that was in a closed container, yet we could move the piston up and down to change the volume. We'll use the same type of concept here. So if we take a system that's in equilibrium, and the chamber is increased, we move the piston up, what will happen is it decreases the pressure as that vapor expands inside of the chamber. At that point, fewer of the vapor molecules are in the given volume, and it causes the rate of condensation. They're not going to bump into each other as frequently. It's going to slow down. And that's going to be that way for some given period of time until the vaporization allows that equilibrium to be reestablished, and it increases the amount of vapor that's present in the system. At some point in time, the rate of condensation is going to, again, increase to the point where it reaches the rate of vaporization and the equilibrium is reestablished. Okay, but it's going to be at the same pressure that it was before. So if we look at this this visually of the piston, so we've got our system that's equilibrium. We got a liquid, and it's got some gas above that, and the two systems or the arrows are the same amount. It's at equilibrium, and we increase the volume. That means this gas expands out into this area. Okay, the larger area there, the larger volume. Now the molecules are not going to bump into each other as frequently. Okay, so what's going to happen is the rate of vaporization is going to increase. The rate of condensation is going to decrease until you produce more molecules in here. And as you produce more and more molecules, the condensation is going to start increasing more and more till it reestablishes the equilibrium you had previously. And the opposite would be true. If I decrease the volume of the piston, so pushed it down, so now what's going to happen is it compresses the gas. They're going to start to collide into each other more frequently. The condensation is going to increase. And it's going to decrease the number of gas molecules as the rate of condensation increases until, again, it reaches that point of equilibrium. So it can respond either way. I can't think that I've made that into a test question. That sounds like a good test question that I need to do. How would a system respond to a change in volume of the piston? Okay, so this is an easier clicker question. Says, choose the compound with the lowest vapor pressure. So now we have to go back and think about the magnitude of the intermolecular forces and what type of things occur in these molecules. So look at these three molecules. Look at the types of bonds that exist. Are the molecules polar? Are they nonpolar? Are they have dipoles? If they do, are there any of them unique dipoles? So compare the magnitude of the intermolecular forces and then tell me which one has the lowest vapor pressure. Something like this absolutely will be the test question and likely a final exam question. Okay, 25 seconds. Seconds. Take one more. Nope, we're in. All right, so, all right, pretty split. So, most of you think A, some of you think, one of you went with B, and then the rest of you went with choice C. So let's think about the types of forces. Okay, what type of intermolecular forces are in A? Let's name our forces off. Does it have a dipole? Permanent dipole? So this is a hydrocarbon. So it's just CH and CC bonds. So the only type of forces we have there are dispersion only. All right, so that's a dispersion only type problem. What about B? What's different from it? It's still got these dispersion forces. So it's this plus, what else is there? The OH is the hydrogen bond. So this OH makes this unique. This is the H bond that's there. All right, it's going to have higher intermolecular forces. Therefore, that one would have a lower vapor pressure compared to A. What's the difference about about C. It still has the same heart to the molecule, still the same number of carbons and hydrogens in there, so it's still got dispersion forces. But not only does it have one hydrogen bond, it's got two of them. So 2 times the H bond. The more H bonds it is, like we talked about the molecule of DNA, the stronger the interaction is going to be. So in this case, the lower the vapor pressure would be the result. Okay. And when you have molecules that can have 3 hydrogen bonds together, typically they're going to be things that have a much higher viscosity than a comparable solvent of similar size that doesn't. So if we look at the example of glycerol, a small molecule that can hydrogen bond, even though its molecular weight is not that high, it has 3 of these OH bonds on it. It's a very, very viscous compound because of that characteristic. And you could take glycerol, has a very, very low vapor pressure. You could take a bottle of glycerol, take the lid off of it, and come back next year and it's 95% of it's still there. Okay, because it doesn't go into the vapor phase, it sticks to each other high. All right, how do we measure vapor pressure? We do it with a U-tube apparatus that looks something like this. So you take and put some liquid in the drawing, and it's hopefully y'all can see that the mercury that's inside of the U-tube is represented by a lighter shade of gray, and I'm just going to highlight. Maybe depending on your angle, it may be hard to see. Hopefully you can see that. But if we have the container exposed and we have a vacuum in here, the 2 would be at the same heights if there's nothing pushing on the tube from this side. So before the vaporization process, it starts at equal heights. But if we put our cork in it at the top or the stopper, and now it allows to establish this dynamic equilibrium between the vapor and the liquid. So now there are gas molecules inside of here, and they're pushing on this height of mercury. We simply measure what this height is to measure out what the vapor pressure is in millimeters, typically millimeters of mercury or inches. Okay, but we simply take a ruler and hold it up to this and make that measurement. So one of the problems that you have in mastering chemistry does something like that when you get to looking at those types of problems. It's a pretty simple apparatus, and we can look at putting this in a controlled environment and change the temperature from a low to high and allow it to reach thermal equilibrium and see how the change in vapor pressure responds to that system. All right, so now when we think about how systems change and how they respond to the conditions, the fact that it can change to the conditions, that's where the term dynamic comes from. It responds or alters whenever the conditions change. So a system that undergoes change, it shifts in a direction that relieves stress or reduces the effects of that change. And that's the inherent nature of all chemical reactions. The reason a chemical reaction proceeds in the forward direction from 2 reactants to make some products is that it's shifting in the direction that has the less stress on the system, and we can think of that stress as energy. Okay, it's the system that has the lowest energy compared to the products. We talked about in Gen Chem 1 how we had energy of systems, and we had 2 reactants that energy at some level and the products at some level, and we could look at going from A plus B to create C. And this would be a case where energy would be given off. Well, if energy, and this is an exothermic system, it's going forward because it reduces the energy in that system. Now, it's not only due to heat energy. We're going to learn that there's something called order that plays a role as well. At the end of this semester, we'll talk about how entropy, another term, comes and plays a role in that too. And it determines our overall predictor if something going to be reactive or not. Okay, so we want to go back and think about this temperature dependence of the vapor a little bit. We know that if we increase the temperature, it increases the number of molecules that have the ability to escape. So the net result is the temperature goes up, we see a change, positive change in the vapor pressure. And sometimes a small change in temperature can make a significant change in the vapor pressure of the molecule. So the rate that it grows depends on the strength of the intermolecular forces. The weaker the intermolecular forces, the more temperature dependent that problem becomes, or that system becomes. So we call this a vapor pressure curve, and it is a plot of the vapor pressure, and we can measure vapor pressure in atmospheres, millibar. Torr is a common way that we do it, versus temperature on the other axis. Okay, so one thing that you need to be able to do is to be able to read a vapor pressure curve. So the thing I've got down there at the bottom. So if I ask you, give you this data, some things that you can read is, if I give you a graph like this, I may ask you what's the normal boiling point. And what the definition of the normal boiling point is when the vapor pressure equals atmospheric pressure. Okay, so if we think of atmospheric pressure as 1 atmosphere, or 760 millimeters of mercury, or 760 torr. So for all of these solvent systems, what happens is the point where the vapor pressure equals atmospheric pressure, that's the boiling point. So diethyl ether, it's right above room temperature. Okay, it's around 35 degrees, and that's what makes it a solvent we have to be careful with. Ethanol, it's at 73 or 78. Water, it's the 100 that we're familiar with. Ethylene glycol, it's not even on the scale. I mean, it's way, way out here. Because this one has very high intermolecular forces, 2 hydrogen bonds that can form. But where we would want to read this at, if I wanted to know what is the vapor pressure of diethyl ether at 20 degrees. Okay, so if I wanted to be able to answer or apply that question, I would simply go to 20 degrees and go up to the line and go over, and it's closest to about 400 millimeters of mercury. And if I needed to convert that from one form of pressure to the other, if I needed to know what it was in atmospheres, I could take 400 torr and divide it by 760 torr per atmosphere, and I could find out what that number is in atmospheres. So I can convert it to different units of pressure if I need to. Key thing is to be able to look at the graph and understand or predict what the vapor pressure is. And you look at old exam questions, I'll give you one of these graphs, and I'll ask what is the vapor pressure at the temperature. Or I may ask you something about which one of these substances has the highest or lowest intermolecular forces. Okay, so which one's going to be the lowest? If I ask choose one of these 4 substances, so diethyl ether, ethanol, water, or ethylene glycol. If I ask which one had the lowest intermolecular forces, which one would it be? Yeah, it'd be the one that's on this side, because it has the lowest boiling point associated with it. The one that's the highest would be the ethylene glycol, because it by far has the highest boiling point associated with it. Okay? So we need to be able to read a vapor pressure curve. And again, if you start covering or looking at the old exam questions in the next week or so, I encourage you, when your study habits, probably by Thursday, I'll post a study guide for the exam that will be the following week. Start looking at the old exams. I encourage you to study ahead. Studies show that you're much better off if you study in blocks of time or the week before versus trying to cram everything into 6 hours or 8 hours the day before. You just retain material much, much better. And that's what you're trying to accomplish in this class. So most of you are here because you want to take a more advanced course in chemistry, or you want to try to get into a professional program. Yes?
Do we need scantrons or anything for this?
You will need to bring a scantron. Yep. So as that gets closer, we'll go over all that. All right, but it does those study habits. Sometimes in your non-majors courses, it may not be as critical that you're studying continuously. When you do your majors courses, it becomes more significant. And I want you to reach your goal of success. You've got to put an effort in on your part, though. So when we talk about something that's boiling, whenever the temperature reaches a point where the vapor pressure is the same as the external pressure, that means is where it's going to become a boiling liquid. So what that means is that the vapor molecules cannot just form on the surface, but they can form anywhere spontaneously inside the liquid. All right, so if you look when you boil water, if you look at the water, it doesn't just happen at the surface. The bubbles form anywhere inside of the liquid, not just on the surface. So that's boiling, and again, when the vapor pressure equals the external pressure, and we'll say for our cases, the external pressure is most commonly around 1 atmosphere, then that becomes the boiling point for the substance. But it changes a little bit when you change its altitude. So the normal boiling point is the temperature we said where the vapor pressure equals 1 atmosphere. But if we change the external pressure, what happens is we lower the boiling point of that liquid. So give you some examples of how the boiling point of water changes at different locations and different altitudes on the Earth. So I like spaghetti, I make a lot of pasta. So one thing you learned is that if you boil things in water at different heights, it's going to change the boiling point ever slightly. So I'll give you a comparison. If you're at sea level, you're at Boston, 20 foot up. Okay, atmosphere is 1 atmosphere of pressure. The boiling point of water is 100 degrees. If you go to Denver, Mile High City, so you're 5290, the atmospheric pressure, as the air gets thinner, you go higher up, it drops 17%, so it's 0.83 atmospheres. The boiling point of water decreases to 94 degrees. Okay, that means you need to cook your pasta 2 more minutes. All right. If you go up to Mount McKinley, so 20,000 feet, the atmospheric pressure is cut in half. The boiling point of water is dropped to 93 or to 83. You're probably going to need to cook your pasta 3 times as long. All right. And if you went to Everest, the tallest point on Earth at almost 30,000 feet, the atmospheric pressure is 1/3 of what it is here on sea level or close to sea level, and the boiling point of water is dropped to 78. So there's actually a temperature or an altitude dependency with the boiling point, but what's changing is the external pressure. The water system's not changing, but the amount of the air column that's on top of that causing the external pressure on top of the water is what's changing. Okay, so we want to look at the heating curve. So we start to heat the liquid up. Now, in Gen Chem 1, we talked about heating curves for substances, and we changed temperatures, and we look at how temperature was related to the amount of heat, the specific heat capacity, and delta T. And we use this equation to calculate the heat lost or gained with the change in temperature. So we have this simple equation that says Q is equal to mass times specific heat times change in temperature. And remember, delta T was simply T final plus T initial. Okay. So, and most commonly, the C sub S is in temperature of degrees Celsius, R degrees Fahrenheit, R degrees Kelvin, and those two temperatures, the change, because this works on the delta T, the one change in a degree for delta C equals 1 degree change for Kelvin. So Kelvin, what that means is Kelvin or Celsius are interchangeable. If it's in Fahrenheit, and if C sub S is not in units of Fahrenheit, you've got to convert that to Celsius. So that's something just to watch for when you're working some of these problems. Now, we looked at last semester simple temperature changes. So when I say simple, you stayed within a given phase. So if I took some water and if it started at 20 degrees and I applied some heat to it, we looked at the changes that occurred as it went to 60 degrees, but it still stayed this low. But what happens when you boil it, as you reach the boiling point, all the heat goes into the boiling of the liquid and the temperature stays constant. So if I have a pot of boiling water at atmospheric conditions, the maximum temperature it can reach is 100 degrees, regardless of how much heat you're putting on it. So if I put some water that's at 20 degrees on the pot, I made some oatmeal this morning, so I did exactly this. It starts heating up to the point where it starts to boil. Once it's boiling, it's at 100 degrees. Now you're just taking the the water and converting it from a liquid state to the vaporization state. So you've got a phase change that's occurring. So whenever you reach a flat line in these curves, the flat line represents a phase change. Okay, in this case, it's vaporization. It's going from a liquid to a gaseous state. So we've got a liquid here. We've got a gaseous state on this side. But whenever it's a flat line, that's a phase change. So whenever all the liquid's been converted into a gas, only at that point does the temperature start to go up. So we get everything in the gas phase, then the temperature of the gas can start to spike up. So which one is most dangerous to you in terms of causing damage? Boiling water versus steam? Steam is much more dangerous. Because steam can, if you have a little bit closed container, you can easily get hit with a shot of steam that's 300, 400 Celsius. Boiling water is never going to be hotter than 100 degrees. Okay, so you can get much more energy in steam because there's no limit on how hot the temperature can get for that system. All right, so one of the problems in mastering chemistry, we're going back and doing something like this, and we're going to work some problems like this tomorrow, but you need to reference table 6.4 back in the textbook to find the specific heat value. So the stuff that we looked in chapter 6 in Gen Chem 1, it's on page 259, and it has the specific heats for the different phases. The reason what that means is that the specific heat for water in the solid phase versus the liquid phase. So solid, liquid, and the gas, they all have different values for the specific heat. So none of those three are equal to each other. And you see for the gas is substantially different. The solid and the liquid are somewhat close together, but the gas is substantially different for specific heat. All right, so now we're going to get mathy. The Clausius-Clapeyron equation. So the Clausius-Clapeyron equation looks at the relationship between the log of the vapor pressure versus the inverse of the absolute temperature. That means it's in Kelvin. And when we plot these two things out, the natural log, Ln, versus the inverse of the temperature in Kelvin, we find the relationship is a straight line. Right? The slope of this line has units. So if we do this for water, and we put natural log of P on this axis and the inverse of the temperature in Kelvin on this axis, we get an equation that describes this. Okay, so we get some data points. We apply a linear curve fit to that, and we find out what the equation of the line is. And what we find is that the slope value is this negative almost 3,500, negative 3478. And the slope is equal to a negative of the change in enthalpy divided by R, where R is the ideal gas constant, so the 8.314 joules per mole degree Kelvin that we talked about earlier in Gen Chem. So what this gives us the ability to do is to measure the vapor pressure at a couple of different temperatures, and from that we can calculate what is the molar heat of vaporization. So let's look at an example of what this equation is. So this is the math behind the Clausius-Clapeyron equation. So the molar heat of vaporization, we said, is the energy required to take 1 mole of that liquid and convert it to vapor state. So on the equation, on the y-axis, we're plotting the natural log of P. On the x-axis, we're plotting the inverse of temperature. So the equation is natural log of P is equal to negative delta H over R plus C. C is the constant. That becomes our y-intercept. And if we look at this data, just pressure versus temperature, this is our vapor pressure curves. But if we take that same data and convert it so it's the natural log versus the inverse of temperature, now these become straight lines. Okay? And that's the relationship we want. If we take and curve fit that, so we curve fit it in Excel, and we get an equation of the line, y equals mx plus b, for a straight line. The slope, the value for m, is equal to negative delta H over R. So that gives us a simple way to calculate what delta H is. So if we want to isolate delta H is simply going to be equal to molar heat of vaporization is going to be slope times R, and it's a negative over here, so we need to change the sign of it. So we do this linear fit, we find out what the slope is, we multiply that by R, the 8.314, change the sign, and we've got the molar heat of vaporization. This is the most common way we calculate the molar heat of vaporization. All right, so let's look at an example of doing this. So I think I gave you one question on the mastering chemistry where you have to go through this process and calculate the molar heat of vaporization. All right, so this is for determine the molar heat of vaporization of dichloromethane and given the vapor pressure versus temperature data. So using the measuring device to measure vapor pressure, they measure the vapor pressure at all these different temperatures. So the vapor pressure in Tor started at 200 degrees, it was 0.8, and at 300 degrees, it went up to 0.9 or 391. All right, so we converted the temperature that was already in Kelvin into inverse of Kelvin by simply going 1 over T, took the inverse of it. So the 200 becomes 0.005, and the same is true for the others. And then on the vapor pressure, we just simply took the natural log of it. Make sure on your calculator you know the difference between Ln versus Log. Ln is base E, Log is base 10. So those two things are, depending on the calculator that you have, Ln is E based. And if it's Log, that means it's log base 10 based. And on this example, we're doing Ln, the E base. So make sure you can do that on your calculator. And when you do those conversions, just to see, if you put in 0.8 and took the natural log of it, you should have got a negative 0.2 on your calculator to see that you can do that. Okay, so now I've got it in the forms that I need. I've got the inverse of K on one axis, the natural log to put on the other axis, and I'll take it to Excel if I want to plot those out. So if I do on the y-axis, I plot it, and the x-axis, I get this linear relationship between these. So now I can take and apply a linear curve fit. I can take Excel and it says, tell me the best curve fit between those data. It's called a least squares regression, and it tells me y is equal to a negative 3,776.7. That represents the slope term. All right, and that's what I need to find out how to go forward with that. And then once I've got the slope term, that's about 3,800. So now I've got the slope. I can take and multiply that to find out what is the molar heat of vaporization. So we said slope M is equal to molar heat of vaporization divided by R. So I plug in my value for the M, take the value for the gas constant 8.314, take and multiply it over to this side. The negative and the negative make it a positive. So the molar heat of vaporization is 3.16 times 10 to the fourth. Or if I want to put it in kilojoules, 31.6 kilojoules per moment. Okay, I want to show you that process right quick in Excel because I'm going to ask you to do one of these. So Excel is the standard tool that we use to do calculations with. So I've taken and opened up a version of Excel, and all I've done is copy these values in for temperature and vapor pressure that we had to start with. Okay, so that's what was given in the table. So I put temperature in column A, and I put vapor pressure in column B. So how many of you had the CIS class in here? CIS 1003. Computers in Society are the BIM equivalent of it. Most of you? You had Tech 1, Tech 2 in high school, or at least the Tech 1 in high school. Use some Excel. All right, so in science, we have to represent data graphically. Excel is the standard tool we use. So if you're not familiar with Excel, I'd encourage you to take, if you hadn't had the CIS 1003, take it immediately, or your next semester get a chance to, because we have the expectation that you can do that. All right, so we go to, I'm going to change my modes here. So if I want to convert 1 over temperature, I just put an equals mark, and then I put 1 divided by, and then I put that column. So what's in cell A2, it's going to say A2, I hit enter, and it does that inversion for me. So the good thing about Excel, once I put a formula in once, I can take and drag it down, and it repeats that calculation. So like in this one, it's if I double click on it, it's taking the inverse of what is in A7. So column A, number 7. So it repeats that calculation going down. Did the same thing for the vapor pressure. So equals the LN vapor pressure, and I'm going to open parentheses, click on the vapor pressure cell, close the parentheses, hit enter, and there's the negative 0.22. I'm going to drag that down and to all the other terms, and it repeats that calculation going down. So the highest value is approximately 6. So that's the data that I want to plot. So to make it plot that data, you highlight the values. All right, so I'm going to go ahead and highlight the titles as well. You go up to insert, and it says insert a scatter plot, and that's the one that you want, and you want the one that's just an XY scatter. So I tell it to do that. That gives me my graph that I want. And then finally, the last thing that I want to do is to insert a trend line. So I've got to get this off of that. So now I can insert a trend line. Click on the data points and right click. Tell it to give me a trend line. And it says, okay, I'm assuming you want linear, but if it was non-linear or something, I could choose something other than that. But I want it to display the equation. And down at the bottom of the page, I'll move it over so we can see it a little easier. It's giving me this equation where it's a minus 37 right at minus 3,800, the same as it was with the other data. So that's the process that you use. So one of the problems in mastering chemistry, I'm asking you to do this on just so you get that learning experience. It's going to be one problem out of 15. If you don't do it, it's not a huge impact on you. The thing that for the exam, I'm not going to ask you obviously to plot this in the exam, but if I give you this graph and give you this equation, so that I want you to be able to look at this and realize this is R. Okay, now I can take that value for R and apply it back to this equation, and I can find out what the value of the molar heat of vaporization is, and that's the likely application you're going to see of this. Okay, so now this is the 1-point Clausius-Clapeyron equation, where we learn how to find out what's the molar heat of vaporization as a function of temperature. So the purpose of this one that we utilize it is what is molar heat of vaporization. Okay, that's how we experimentally determine it. Okay? All right. So you don't have time to work this problem coming in or today, finish it up, but just I'll let you look at what I'm going to ask you to do. The start of class on Wednesday. It says the graph's prepared, the natural log of vapor pressure versus the inverse of temperature. You've got the slope, and I want you to tell me what the molar heat of vaporization is. You do. I mean, that doesn't take a minute to do. So answer this real quick. So this is the same thing that we just did. So you've got the slope. I'll even here's your equation. Gave you the value of R. Remember what we did on the previous one? It was in joules. We had to convert it to kilojoules. Because the units of R are joules. all of these answers are in kilojoules. So. All right, once you put your answer in, you're free to go for the day. That way some of you are cranking it out. I'll give you another minute or two, but our time's over. Make sure you put your lab reports back in the back. There's a stapler over there. Put your handwritten paper on top. Yep. Thank you. Everybody thought it's between A and C. All right, B.